I promised a more advanced method, namely here policy gradient for episodic Markov decision processes. So again, episodic MDPs are not infinite length, but either we terminate after some maximum number of steps, or we terminate when they've reached a natural end, like the robot falls or whatever has gone wrong. So we are looking for a parameterization theta of our actions that will give us the greatest expected reward. And in what follows, I'll use the shortcut tau for a rollout of a trajectory. So a system that was in a particular state at time 1, and a particular action was taken, a particular reward was earned, and so on. And now we will sample a couple of trajectories from a given policy, and we will evaluate the reward of those trajectories under this policy, and then we're interested in the gradient with respect to the parameters. And then we can do gradient ascent in reward space. So we use, just like we did gradient descent to minimize the loss, here we do gradient ascent to maximize the reward. So we find new parameters, theta nu, which are all parameters plus some magic step size times this estimated gradient. And just like with gradient descent, we can do all the usual tricks here. It's important to not walk too far, because even if you started at sort of decent parameters and then you walk too far, you may end up with a system that no longer does anything useful. So adaptive step size control is important, and you can use things like Atom. You can also, it helps to not find the gradient but the natural gradient. So many of the things that we've seen also apply in this setting. But now we need to estimate this gradient of the expected reward first. So this is just the definition here. The reward is multiplied. We compute the expected reward here, and here we have a probability of trajectories given a specific parameterization. Then under mild assumptions, we will exchange here the integral and the differentiation. And then this is a trick that we've seen before when we looked at the Fisher information and so on. We will multiply and divide by this probability, and then rewrite this probability as the gradient of a log. And so gradient of a log will give us the gradient of the probability divided by here the probability, which is what we have on the right hand side. Okay, so this is how far we got, and then this can again be written as an expectation, which is now approximated empirically rather than take an expectation here over all trajectories. We just sample trajectories and then sum over the rewards that we find in these trajectories. So here we have summation over the rollouts indexed by I. Each rollout gave us a particular reward, and we can also for each rollout compute this second term here, the gradient of the log probability. Why? Because now here the probability of an entire trajectory is again factorized using this probabilistic graphical model that we've seen. Yeah, so each random variable is conditioned on only its parents and not on its grandparents. So this is just the factorization that we've seen before. But now note that on the right hand side only one of these terms depends on theta at all. So this one depends on theta, but the others do not. So when we now take the log of this, then this product becomes a summation over log terms. And if we then take the gradient with respect to theta, then only this term here survives. This is really important because this is where the world model was. Yeah, so this one and also this one here. The first expression tells us if we were in state such and such at time t-1, and then we took such and such action at time t-1, what's the probability distribution over states at the next time step? And this we don't know, but here it simply drops out. Same for this. If we are in such and such state, we take such and such action, how big is our reward going to be? If the reward is stochastic. This is also, when we differentiate with respect to theta, becomes 0. So overall, we find that it simplifies like this. The gradient of the log probability is the gradient of the sums over logs of only the probabilities of a specific action starting from a specific state. And if now we use this equation here, and if we use that equation here, then we find that overall the gradient of the expected reward can be summarized as is written here. Gradient of the expected reward can be approximated like so. Yeah, so I have a summation over all rollouts. I look at a particular rollout or particular realization, how well it did, and then weight this with the gradient of the log of the probability of the action that was taken given the state that the system was in and given my parameters that define the policy. So what we have is a neural network, or we can use a neural network here. It has parameters theta. It ingests a state S, and now for a given state, it needs to emit a probability distribution over actions. So if the system can take 10 possible actions, then we would have 10 output neurons, and the neural network would only suggest a probability with which each of these 10 actions should be taken. And now one of these actions was actually taken, and then we evaluate if it was a good action. Then this gradient will tell us how would we need to change the parameters in the network so as to make this action even more likely in the future. So what we have overall is rewards of trajectories. Now, what we have are gradients that tell us how would we make the specific series of actions that was chosen, how would I need to change the parameters so as to make this set of actions more likely. And all of this is weighted by, well, and how good was this trajectory in the first place? So if the reward was poor, then there is no motivation to make these actions here more probable. But if the reward was high, then there is a great incentive. This works, but this gradient estimate can be very noisy. And so much research has been poured into making this estimate less noisy. And here are two suggestions. Let me start with the second, which is more relevant. The suggestion here is to take the formula that we had above, but subtract a constant, a baseline. So just qualitatively, it says, again, this tells us how we would need to change the parameters so as to make a particular trajectory more likely. And here we do the following. We ask if this trajectory was better than average. Let's say B here is the average reward or the baseline reward. If this trajectory was above average, then indeed we want to move in this direction. If the trajectory was sub-average, then actually we will be pushed away from this direction and we will move away from this bad region of parameter space. So if you remember the simple algorithm that we had before the break, there we only kept the top 10% of the performing parameters and we simply ignored the other ones. Here the bad ones can even push away the new parameter estimate from the poor ones. Now, why is there an equality here? Why is it okay to subtract a constant? This is explained here in the next few lines. Let's just look at this extra term here. So the expectation of some constant times here the gradient. This is what's written here. Then the expectation is written out. This is the definition of the expectation. The P cancels. The gradient operation is pulled in front of the integral, and so is the constant. And then what we have is an integral over a probability distribution, which is 1, a constant, so its gradient is going to vanish, and hence we can use any constant here that we want. A typical choice would be to take the average performance. So to look at all rollouts and see what was their reward and take that as a baseline. That's the reinforced algorithm. Also quite old already, from the 80s maybe. Okay, any questions about reinforce? Any questions about policy gradient in general? Yeah?
So the expectation reverse, if we minus the baseline, still doesn't change. How about the variance? Is it possible that we sample different trajectories, the variance is not stable and is might really big?
Yes, like you say, the variance of this entire estimator is really large. So this is why this other school of algorithms that we have not talked about today, the class of algorithms that tries to estimate the value, they do not use concrete rollouts. Instead, they try and fit a world model from which you can read off precisely how good a particular policy is. The problem is that this fit of a world model, of a nonlinear world model, might be complicated or is only approximate in itself. But yes, that is one way forward. So like you say, this is an extremely noisy estimator. So many iterations may be needed. And this is why these variance reduction strategies are important. But even with them, you may still need many iterations.
And how many iterations do we need in practice for concrete plan? Or it
Oh,
depends?
it of course depends on how high dimensional your parameter space is and how nonlinear the behavior of your system. Hundreds to thousands to billions. Yeah. So these robot walking examples that you often see, or learning to balance a pole or something, these are typically hundreds of iterations. And if you want to beat the best Go player in the world, then it's millions of iterations. So the system played, I think, billions of games against itself. Okay, here's a second strategy. So if we look at this line here again, this is just the definition, where this time the total reward has been written out. If the total reward is a sum of rewards garnered at individual time steps, then this equation holds. And now there's one crucial observation, namely, let's say the reward at time step 10 will not depend on the action and on the state in step 20. Yeah? And so we can sum only over the terms that are truly relevant. The next equation here is just a rewrite of the previous one, where the second factor has been pulled into each of the summation terms that we saw. And now in this diagram here, I tried to show we have now two indices, one index for t and one index t prime, that for a given value of t prime, all entries here, so all of this will be multiplied with the same reward, r of t prime. So this is what we have in the columns here. And vice versa, the term, for example, the terms marked here in red, they're always the same, no matter which the reward. So what we can do is we can take these terms and multiply them with the respective rewards that are valid at time t prime. And then sum only over the terms that are meaningful. Yeah? So we don't start summation here, but we only start summation at this point, which also helps eliminate terms that only contribute to noise. Okay, so big picture and references. We have today talked about strategies with and without using the gradient to estimate the optimal policy. And there are a couple of video lectures, for example, by Schulman and Abel about this. If you want to read one single thing about reinforcement learning at all, then I would recommend the blog from Karpathy. The title is something like From Pixels to Pong, and it explains both some of the science in policy gradient, but also has some more general thoughts. I also like the Jan Peters article on policy gradient on Scholarpedia. By the way, he made his scientific name by replacing standard gradient with natural gradient. Yeah, so this is a good idea in this field here also. And then there is a complementary line of work. There is a relatively slim book by Stepesvari about the dynamic programming and the extensions needed when you go to unbounded Markov decision processes. Also, there is a 2015 David Silver course, which talks a lot about these methods that try and estimate the value of a given state. The best known overall reference is the book by Sutton that I already mentioned, which is also available online as a PDF on his website. And more recently, these two schools have come together in the actor-critic methods. So they go back, I think, to the 90s, but have gained in popularity recently. And like I said, AlphaGo 0 is a good example because they have a single network that uses, just this one set of parameters to both estimate the value of a state and what would be the optimum next action to take. But then, in addition, need a Monte-Carlo tree search to follow over a few steps and see, to essentially refine these estimates of the neural network for the value and of a state and of an action. Okay, this much on reinforcement learning. There are a couple of arenas that have been published. So these two, for example, where you find all the infrastructure for creating, robots like these, or some of these are computer games. And in these gyms or arenas, you can then drop in your own reinforcement learning algorithm or your modification to an existing reinforcement learning algorithm without having to worry about the infrastructure so much. So these are good benchmarks and have made work in this field a lot easier. Okay, with that, I'm closing for today. It's all I want to say today about reinforcement learning. I'm still making up my mind if we'll have more of this next week or something completely different.